Tonight, we're going to zoom out farther than any spacecraft has ever travelled, not just beyond the solar system, but beyond our entire galaxy. Imagine pulling back from Earth, past the planets, past the Milky Way's bright disk, until the familiar spiral of our home fades into a tiny speck. Keep going, hundreds of millions of light years, until something unsettling appears on the largest map of space humans have ever drawn. Our whole neighbourhood looks empty. Astronomers mapping nearby galaxies discovered that the Milky Way doesn't sit in the middle of a crowded cosmic city. Instead, it seems to lie in or right next to a vast underdense region, a place with fewer galaxies than expected, stretching hundreds of millions of light years across. On the grand scale of the cosmic web, with its glowing filaments and massive clusters, our location looks like the inside edge of a bubble carved out of space. That should not happen. On large enough scales, the universe is supposed to be uniform, the same in every direction, wherever you stand. That principle is baked into the equations that describe cosmic expansion, dark energy, and the age of the universe. But detailed surveys show a contradiction. The cosmic microwave background, the ancient afterglow of the Big Bang, is smooth to about 1 part in 100,000, while our local region right now looks unusually empty. Expectation, a typical patch of the cosmic web. Reality, an underdense pocket that behaves like a cosmic void. This isn't just a cartographic curiosity. If our local space is less dense than average, it can change how fast nearby galaxies appear to recede, the same way wind can change the apparent speed of an aircraft. That means measurements of the Hubble constant, the rate at which the universe expands, could be biased by our position. Some scientists have even proposed that this local underdensity might help explain the Hubble tension, the growing disagreement between expansion rates inferred from the early universe and those measured in the nearby cosmos. Suddenly, where we live in the universe is not just a backdrop, it's a suspect. If our region is special, it could be tricking us about how old the universe is, how fast it's growing, and even whether the standard laws of cosmology are complete. No one predicts that a random observer should wake up inside a suspiciously empty pocket that quietly distorts the view of the rest of space. Yet here we are. So the central question becomes unavoidable. Why are we inside an isolated cosmic pocket when the rest of the universe, from the smooth microwave background to distant galaxy surveys, looks different? Is this a fluke, a selection effect, or something life requires? Before we get started, understand that this is not just about one void on one map. By the end of tonight, you're going to understand how voids sculpt the cosmic web, why our measurements of expansion are in crisis, and whether our lonely bubble is an accident or a clue. So, here's the rule the universe is supposed to follow. On large enough scales, nothing is special. No favoured locations, no privileged directions. To cosmologists, this is almost sacred. It's called the cosmological principle, and it says that if you zoom out far enough, the universe should look the same everywhere, and in every direction, like a perfectly well-mixed soup stretched across space. That principle is powerful. It lets scientists treat the cosmos as one smooth fluid, write down neat equations for expansion, and connect what spacecraft and telescopes see near the solar system to what happened just after the Big Bang. When the cosmic microwave background is measured and found to be uniform to about 1 part in 100,000, it feels like a direct confirmation. At early times, the universe really did look bland. No one predicts wild local exceptions when you average over hundreds of millions of light years, but then the maps arrive. Galaxy surveys start to trace where the mass actually is around the Milky Way. And the picture that emerges is not a smooth soup. It's a cosmic web, bright filaments, dense clusters, and in between, huge dark voids where very few galaxies live. When those surveys focus on our region, they discover something unsettling. Our galaxy appears to sit on the edge of, or partly inside, a vast underdense region often called the local void, or KBC void. This isn't a tiny gap. Some reconstructions suggest a region hundreds of millions of light-years across, where the galaxy density is significantly lower than the cosmic average, designed for a universe that should be statistically uniform on those scales. The cosmological principle suddenly has to confront a neighbourhood that looks emptier than it should be. And that emptiness has consequences. If the local region has less matter, gravity pulls less strongly, and the space here can expand a bit faster than the global average. That means nearby galaxies, supernovae, and standard candles used to measure the Hubble constant might all be sitting in a slightly over-eager patch of expansion. The boundary between local and global becomes blurred. Are we misreading the true expansion rate of the universe because our measuring sticks live in a void? If that's true, then the inferred strength of dark energy could be biased. The apparent tension between local Hubble measurements and the value extracted from the cosmic microwave background might not demand new physics at all. It could be a sign that our region is unusual. No one expects the address of the solar system to matter for fundamental cosmology, yet the local void whispers that it might. Tonight, we're going to take that whisper seriously. To do that, there is a 7-step mission. First, map the cosmic web structure and see how filaments, clusters, and voids really partition space. Second, dive into void physics, how underdensities grow, how fast they expand, and how they push on their surroundings like a negative gravitational wind. Third, build a detailed local map of our own environment, the local group, nearby filaments, and the KBC void. Fourth, confront the Hubble tension and ask whether a local underdensity can truly shift the expansion rate we measure. Fifth, compare our pocket to the cosmic microwave background, the pristine snapshot of the early universe that lives far beyond our local irregularities. Sixth, test everything against large cosmological simulations, where millions of virtual galaxies evolve and voids either appear naturally or don't. And seventh, push into anthropic reasoning, whether observers are more likely to find themselves in special regions, and what that means for how typical the Milky Way really is. By the end of tonight, you're going to understand why the old picture of a bland, average cosmic neighbourhood was wrong. Our corner of the universe is stranger, emptier, and more structured than the textbook suggested. The question is not just whether we live in an underdense pocket. The question is how special that pocket truly is, and whether the rest of the universe far beyond our void is playing by the same rules. Now, let's begin. Our corner of the universe might be stranger, emptier, and more structured than the textbook suggested, but that's exactly why this channel exists. Here, the mission is to follow that weirdness wherever it leads, from the edge of the solar system out to the largest scales that space can offer. Tonight, we're going to treat this isolated pocket question as one chapter in a much bigger journey. One episode might ride along with a spacecraft skimming the boundary of the heliosphere, watching the solar wind fade into the interstellar medium. Another might zoom out hundreds of millions of light-years to trace the cosmic web, the filaments, clusters, and voids that decide where galaxies live and where they don't. Because once scientists discovered that the universe is not a random sprinkle of galaxies, but a vast foam of dense walls wrapped around enormous voids, everything changed. Suddenly, questions about the local void, the KBC void, and whether the Milky Way is sitting in an underdense bubble stopped being trivia. They became part of a bigger puzzle that connects to the Hubble tension, the age of the universe, and even anthropic reasoning about why observers like you exist here at all. If hearing that our galaxy might be floating in a cosmic void sends a little jolt of curiosity through you, then you are exactly who this channel is for. This space is built for people who want to understand why the solar system orbits in a particular arm of the galaxy, why our local group sits on a filament instead of deep in a cluster, and what that says about the rest of the cosmos beyond our neighbourhood. Before we get started with the detailed history, a quick request. If you're enjoying long-form dives into questions like the cosmic web, the Hubble tension, and what the cosmic microwave background really tells us about the rest of the universe, take a second to like this video or subscribe. It's a tiny action, but it has a real impact. Engagement tells the algorithms and the humans planning the next mission of this channel that high-effort explorations of deep time, deep space mysteries are worth the energy. No one expects a video about underdense regions and selection effects to compete with viral clips. No one predicts that a careful explanation of why living in a void might bias our measurements of cosmic expansion will travel far. Yet absolutely no one anticipates how much that support helps justify the next big investigation. By the end of tonight, you're going to understand why our isolated pocket ties directly into how we map the universe itself. So to see where this all began, we need to rewind. Back to the first galaxy surveys when astronomers pointed telescopes into what looked like empty darkness and discovered a pattern far stranger than anyone imagined. Now, let's begin. In the early 20th century, when telescopes first resolved those mysterious spiral smudges, scientists called them island universes. Each galaxy was its own self-contained archipelago of stars, drifting in a vast, dark sea. On the largest scales, there was no clear pattern, no obvious architecture, just scattered points on flat photographic plates like random grains of salt thrown across the sky. The maps reflected that mindset. You had right ascension and declination, angles on a dome, beautiful charts, but they were only two-dimensional shadows of a three-dimensional reality. There was no reliable way to tell which galaxies were nearby and which were far beyond, stacked along the same line of sight. To understand the true layout of space, astronomers had to do something radical: turn the sky into a volume. That pivot came with redshift. As the universe expands, light from distant galaxies is stretched, shifted toward the red. Measure that shift. Use Hubble's law, and you get distance. Suddenly, a simple dot on the sky could be given depth. The flat star chart becomes a 3D map. Tonight, we're going to follow how that single idea transformed a random sprinkle into a hidden skeleton. Early redshift catalogues were tiny, a few dozen, then a few hundred galaxies. Hints appeared. Pairs, small groups, clusters, but the big picture stayed blurry. Then, in the late 1970s and early 1980s, the CFA Redshift Survey pushed through the boundary. Thousands of galaxies mapped not just in angle but in distance, carved into slices through the cosmos. Expectation, a nearly uniform fog of points. Reality, something far more dramatic. In those famous wedge diagrams, galaxies didn't fill space evenly. They traced arcs, walls, and dense knots. And between them, cavities, huge, nearly empty regions, tens of megaparsecs across. No one expects that the universe on scales of hundreds of millions of light years will start to look like a sponge. No one predicts that galaxies will outline filaments and sheets while gravity evacuates the gaps. Then came the Sloan Digital Sky Survey, a dedicated mission, a robotic telescope scanning the sky night after night, turning millions of galaxies into precise 3D coordinates. The pattern sharpened, filaments stretching like intergalactic highways, clusters at their intersections, the massive city centres of matter, vast voids in between where the density of galaxies drops to almost nothing. The cosmic web was no longer a metaphor, it was an observed structure. By the end of tonight, you're going to understand why that web matters for our isolated pocket. Because when those maps were overlaid with our own position, something unsettling appeared. The Milky Way does not sit at a blazing node of the largest superclusters. It lies on the fringe skirting the edge of an underdense region. One of those vast cavities, what is now called a void, seems uncomfortably close to home. So the question becomes unavoidable. If the universe is a web, why are we living near one of its holes? If the universe is a web, then to answer why we live near one of its holes, you first have to see how that web is actually woven. Tonight, we're going to zoom out until individual galaxies blur together and only the grand architecture remains. Now, let's begin. At the nodes of this architecture sit the giants, galaxy clusters. These are not quiet neighbourhoods, they are crowded cities of space, where hundreds or even thousands of galaxies are bound together by gravity into a single massive system. Between those galaxies, the space is flooded with gas, heated to tens of millions of degrees, glowing in X-rays that spacecraft and orbital observatories can detect. The visible galaxies are just the bright decorations. Most of the mass is dark matter, creating deep gravitational wells that lock the whole cluster in place. Those clusters do not float in isolation. They are connected by filaments, elongated bridges of dark matter, gas, and galaxies stretching over tens to hundreds of megaparsecs. Think of them as the highways of the cosmic web, channels along which matter has flowed for billions of years. In these filaments, galaxies line up like streetlights along an invisible spine. When scientists map their positions, the pattern is unmistakable. Thin, curving strands linking one dense knot to another, forming the backbone of structure that extends far beyond any single solar system or group of planets. But the most striking feature is not what is full, it is what is empty. Between the clusters and filaments lie the voids, vast regions with far fewer galaxies than the cosmic average. Some span 50, 100, even 200 megaparsecs across, that is hundreds of millions of light years from side to side. No one expects those regions to be perfectly empty, and they are not. There is still dark matter, there is still thin gas, there are still a few lonely galaxies drifting through. Yet compared to the crowded filaments, a void is a desert. A useful picture emerges if you imagine soap foam. The clusters sit where the walls of the foam meet, at the junctions. The filaments are the thin, shimmering walls themselves, and the voids are the bubbles, the hollow interiors. By the end of tonight, you're going to understand that the Milky Way is not at the centre of a great knot, but near the edge of one of these cosmic bubbles, pressed up against a low-density region like a galaxy on the wall of a cell. This entire foam-like pattern is not imposed from outside. It emerges naturally from gravity acting on tiny initial ripples in the early universe. No one predicts the exact position of each void in advance, but simulations that start with those minuscule fluctuations and let gravity pull, merge and collapse over billions of years grow their own clusters, their own filaments, and their own great empty regions. Absolutely no one anticipates how closely those simulated webs will resemble the one we observe, down to voids very much like the one next to us. And that is where the mystery of our isolated pocket truly begins. Those simulations of filaments and voids look abstract on a screen, but you live inside one tiny knot of that web. Tonight, we're going to zoom in until that grand lattice of space turns into a recognizable address. Now, let's begin. In the middle of one filament, there is a modest little association of galaxies bound together by gravity. Astronomers call it the local group. It is not a rich cluster blazing with thousands of giant galaxies. It is a small gathering. The Milky Way, Andromeda, the Triangulum Galaxy, and a few dozen dwarf companions, all orbiting a shared centre of mass like slow, sprawling planets in a scaled-up solar system. On human scales, the local group is impossibly large. On cosmic scales, it is tiny. From one end to the other, it spans roughly 10 million light-years. Light, leaving a star on one edge, takes 10 million years to reach the far side, crossing a volume that would swallow every planet ever visited by a spacecraft and still look empty. Yet compared to the superclusters and voids those simulations revealed, regions hundreds of millions of light-years across, this entire domain is just a speck. Expectation, a lonely island adrift in nothing. Reality, the local group is wired into something bigger. Beyond its outskirts, galaxies begin to thicken into the Virgo cluster, a much richer city of space with thousands of members. That cluster, in turn, is one node in the broader Virgo supercluster, and even that is not the end of the map. By tracing the motions of galaxies, scientists discovered an even grander basin of attraction. The Laniakea supercluster, a continent of matter over 500 million light-years wide, within which the Virgo supercluster and our local group are just small neighbourhoods. So we are not completely isolated. Our galaxies feel the gravitational pull of this larger landscape. Streams of galaxies flow along filaments toward massive clusters, like rivers following a slope. The cosmic web channels motion, growth, and the invisible wind of gravitational infall. But here is the twist. The local group does not sit deep inside a dense cluster. It lies near the boundary of a large underdense region known as the local void. On one side, toward Virgo and Laniakea, space gets busier. More galaxies, more mass, more structure. On the other side, there is a yawning deficit of galaxies stretching tens, even hundreds of millions of light-years. No one predicts that the Milky Way should be perched right on that gradient, half-tied to a bustling region half-facing a relative emptiness. By the end of tonight, you're going to understand why that boundary might be more than a cartographic curiosity. If our local group is sitting on the edge of a vast cosmic hollow, does that distort how we measure the expansion of the universe beyond, how we read the afterglow of the Big Bang, how we interpret those simulations that looked so reassuringly familiar? Or is this edge of void address a coincidence that hides a deeper, stranger selection effect still to be uncovered? To answer that, you have to step through an invisible doorway next to our cosmic house. Tonight, we're going to walk into what astronomers call the local void and see why the room beside us is so eerily empty. Now, let's begin. When scientists map nearby galaxies in 3 dimensions out to tens of megaparsecs, they expect a kind of lumpy uniformity. Filaments here, clusters there, but no giant one-sided holes. Instead, they discovered a yawning asymmetric gap in one particular set of directions adjacent to the local group. Dense walls of galaxies on one side, a cavernous underdensity on the other. That underdense region is the local void. It is not a perfect sphere, not a clean boundary like a planetary orbit, but a sprawling section of space where the number of galaxies drops far below the cosmic average. Imagine flying outward from the solar system and leaving the familiar web of clusters behind, only to find that for tens of millions of light years, the sky of galaxies thins out, like walking from a crowded city into a dark, nearly empty desert. How was this emptiness inferred? Not by seeing nothing, but by seeing too little. Galaxy surveys such as 2MASS and later redshift catalogues let spacecraft and telescopes build 3-dimensional maps of the local universe. Plot every known galaxy within about 100 megaparsecs, color-code their distances, and a pattern appears. On one side of the Milky Way, the points swarm into filaments and nodes. On the local void side, they fall away, leaving a lopsided gap where, statistically, many more galaxies should be. Then comes a pattern interrupt. The local void is small in cosmic terms, tens of megaparsecs. But some researchers argue that our underdense neighbourhood is only the inner hollow of a much larger bubble. This is the proposed KBC void named for Keenan, Barger, and Cowie, stretching roughly 300 megaparsecs across. In that picture, the local void is like the closest empty room, while the KBC region is the entire low-density wing of the building. By the end of tonight, you're going to understand why that scale matters. Over hundreds of megaparsecs, the universe is supposed to smooth out. Yet measurements of galaxy counts, infrared light, and peculiar velocities suggest our broader region might be 20 to 50% less dense in matter than the cosmic mean. Not empty space, but thinned-out space, where the cosmic web's filaments are present, just lighter, more widely spaced, carrying fewer galaxies per cubic megaparsec. No one predicts this in a perfectly idealized homogeneous universe, but in a real lambda CDM cosmos, rare underdensities of this size can exist. And if the Milky Way sits inside such a bubble, there is an unsettling implication. Local supernovae, nearby galaxies, and the way their light stretches as space expands could all be subtly biased by our underdense surroundings, without announcing that bias on the sky. No one expects their own neighbourhood to be the optical illusion. Yet if our region is expanding a bit faster than average because gravity has less mass to fight against, then the local Hubble constant, measured out to a few hundred megaparsecs, might not match the value inferred from the cosmic microwave background, which averages over the denser universe beyond our bubble. One number could be the universe as it is here, the other, the universe as it is almost everywhere else, and absolutely no one anticipates how far that possibility reaches. If our galaxy lives in a giant underdense pocket, then every distance ladder, every calibration that leans on nearby galaxies could be leaning on a slightly slanted floor. The next question is brutal and simple. Can a void like this truly mimic new physics, or does the rest of the sky refuse to cooperate with that escape hatch? To answer that, you have to do something that sounds impossible on its face. You have to weigh emptiness. Tonight, we're going to turn blank regions of space into measurable objects and see whether our own cosmic neighbourhood really is sitting in a sparse pocket of the universe. Now, let's begin. When astronomers talk about mapping the universe, they are not just drawing a flat star chart. They build 3D maps. Each galaxy gives two angles on the sky, like longitude and latitude, and one more coordinate. It's redshift. The spectrum gets stretched by the expansion of space, and that stretch acts as a rough distance marker. Put millions of these points together from a single survey, and an invisible web appears, bright knots where galaxies pile up, dark tunnels where almost none exist. Redshift surveys like the Sloan Digital Sky Survey and TUMAS turned this from theory into terrain. Designed to be all-sky censuses of galaxies, they let scientists fly, virtually, through hundreds of millions of light-years of the cosmic web. The contrast is sharp. Filaments and clusters blaze with galaxies. In between, there are volumes where the counts plummet. Those are the voids. But a void is not just a place that looks empty. It is defined statistically. Take a region of a given size, count how many galaxies live there, and compare that number to the cosmic mean for the same volume. If the number density falls below a chosen threshold, say 20 or 30% of average, that region qualifies as a void. Change the volume, change the threshold, and the catalogue of voids changes. The mission is to choose those parameters so the pattern matches what gravity in our standard cosmological model predicts. Closer to home, something interesting happens when this method is applied. Using SDSS, TUMAS, and dedicated local catalogues, astronomers find that the Milky Way is not sitting in the middle of a massive cluster. It lies near the edge of a large underdense region often called the local void, and possibly inside a broader KBC-scale underdensity stretching hundreds of millions of light-years. No one expects the average universe to be sampled from such a low-density pocket, yet that is what the counts suggest. There is another way to weigh nothing. Watch how galaxies move. Beyond the smooth Hubble expansion, galaxies have peculiar velocities, extra motions as they fall toward overdense regions and drift away from voids. Surveys like cosmic flows measure distances independent of redshift, then compare those distances to the observed redshifts to extract these peculiar motions. The result is a velocity field, a kind of gravitational wind map showing where space is being pulled and where it is relaxing. In that flow pattern, the local void leaves a fingerprint. Nearby galaxies show a tendency to stream away from the empty region and toward denser structures like the Virgo cluster and the so-called Great Attractor. Prediction versus observation again, models with an underdensity around us reproduce the flows more cleanly than models with a perfectly average neighbourhood. By the end of tonight, you're going to understand that this is not a guess about emptiness. It is a set of measurements, galaxy counts, redshift maps, and peculiar velocities, all converging on the same unsettling verdict. Our corner of the cosmic web looks a little too quiet. The next step is harsher. If our local pocket is underdense, can it really fake new physics? Or does the rest of the universe, from the planets we orbit to the microwave afterglow beyond, push back against that escape route? If our pocket of the cosmic web is unusually empty, the next question hits hard. How do you even tell how fast the rest of the universe is pulling away from you? That's where one number suddenly becomes the main character, the Hubble constant. Now, let's begin. The Hubble constant is the current rate at which space itself is expanding. It tells you how fast distant galaxies recede per unit distance, usually in kilometers per second per megaparsec. 1 megaparsec is about 3.26 million light-years. So a value of, say, 70 means that for every megaparsec away a galaxy is, it appears to be moving away 70 kilometers per second faster. It's the master ruler for cosmic expansion, setting the scale for the age, size, and future of the observable universe. But a ruler in space is only useful if it can be calibrated. Locally, scientists build that calibration using a distance ladder. They start with nearby stars whose distances can be measured by geometry, then move to standard candles, like Cepheid variable stars in nearby galaxies. These stars pulse with a brightness pattern that reveals their true luminosity. Compare that intrinsic brightness to how faint they look, and the distance drops out. Those Cepheids then calibrate Type Ia supernovae, explosions so uniform in peak brightness that they act like cosmic beacons scattered across hundreds of millions of light-years. From there, the mission is clear. Measure supernova distances, measure galaxy redshifts, fit a line, read off the slope. That slope is the local Hubble constant. Modern distance ladder projects land on a value around the low 70s in kilometers per second per megaparsec. The error bars have shrunk. The confidence has grown. And no one expects what happens when this local ruler is compared to the one inferred from the early universe, because there is a second way to measure the same thing, and it lives far beyond our neighbourhood. The cosmic microwave background is the cooled afterglow of the Big Bang, a nearly uniform sea of microwave light with tiny temperature ripples. By the end of tonight, you're going to understand why those ripples encode a full cosmological model. How much dark matter, how much dark energy, how curved space is, and, crucially, what the Hubble constant should be today if that model is right. CMB missions like Planck read those ripples and, using the standard cosmological model, predict a Hubble constant in the high 60s, not 73, not 74. The boundary between close enough and something is wrong has been crossed. The discrepancy is now many times larger than the quoted uncertainties. No one predicts that two of the most precise rulers in cosmology would refuse to agree. This is the Hubble tension. Early universe predictions versus late universe measurements, both precise, both careful, both in conflict. So the question turns back to our isolated pocket. If we live in an underdense region, less matter, weaker gravity, faster local expansion, could that cosmic bubble make galaxies around us appear to race away faster than the true cosmic average? Or are we about to discover that even blaming the void is not enough, and something deeper in the universe is quietly breaking our rulers? So imagine this. The universe has one true expansion rate written into the fabric of space since the cosmic microwave background first cooled. But inside a giant underdense bubble, with less matter tugging back, the local expansion can subtly outrun that global pace. Less gravity means less braking. The same underlying cosmic engine, but with the parking brake slightly released in our neighbourhood. Now, let's begin. In a perfectly uniform cosmos, every observer would measure the same Hubble constant once they average over large enough scales. Double the distance, double the recessional speed, no matter where you stand. But the real universe is lumpy. Filaments, clusters, and vast voids carve a cosmic web, and that structure bends the flow of expansion. Inside an underdense region, galaxies feel weaker gravitational pull from their surroundings, so they drift apart a little faster than the cosmic average. Tonight, we're going to follow that idea to its unsettling conclusion. If observers live inside a large void and only use relatively nearby galaxies to build a distance ladder, they will infer a higher Hubble constant than observers embedded in a more typical, denser region. Same universe, same underlying physics, different apparent expansion just because of where the measurement is taken. This is where the KBC void proposal enters the mission profile. Some scientists have suggested that the Milky Way might sit inside a roughly 300 megaparsec scale underdensity, often called the KBC void or local hole. In that picture, the solar system occupies an unusually empty bubble, surrounded by denser shells of galaxies beyond. When local supernovae and Cepheids are used to calibrate distances, that underdensity could bias the result upward, making the local Hubble constant look faster than what the cosmic microwave background implies. Pattern interrupt. This is not just a theoretical game. Surveys mapping galaxy counts and peculiar velocities really do hint that our region may be underdense compared to the cosmic mean. No one expects a perfectly smooth distribution, but the question is scale. To fully bridge the current Hubble tension, the required void has to be very large and significantly emptier than average. Large enough that, in standard cosmology, no one predicts many such regions. Absolutely no one anticipates living in one by accident. By the end of tonight, you're going to understand why that makes cosmologists nervous. If the KBC void is real and strong enough, it could explain a fraction of the Hubble tension, trimming a few kilometers per second per megaparsec off the disagreement. But most detailed simulations and reconstructions suggest it cannot do the whole job without pushing against what the lambda CDM model normally produces. Our isolated pocket may be part of the story, not the entire script, so the narrative shifts. Maybe local underdensity is a systematic we must subtract, or maybe its very existence signals that our position in the cosmic web is rarer than expected. In the next section, the focus turns from expansion rates to odds. How improbable is our pocket, and what does that improbability say about the universe beyond our boundary of observation? To know how rare our pocket might be, the story has to rewind, far beyond our local void, far beyond the present-day cosmic web, all the way back to a universe where there were no voids at all. Now, let's begin. Picture space when it was less than a few 100,000 years old. No galaxies, no planets, no stars, just a hot, blinding plasma, photons, electrons, and baryons jammed together in a dense, glowing fog. The entire observable system is almost the same temperature everywhere, with density variations so tiny they would look perfectly flat to the naked eye. From a distance, it seems featureless, but on quantum scales, nothing is perfectly smooth. During inflation, when space itself expanded faster than any wind or wave could cross it, microscopic quantum jitters were stretched to cosmic size. Tiny fluctuations in energy became tiny over and under densities in matter. The contrast is minuscule, 1 part in 100,000, but gravity does not forget. Those seeds are the blueprint for every cluster and every void that will ever exist. Before we get started on the cosmic microwave background, there is one crucial detail. In this early era, photons and matter are locked together. Every time an electron tries to clump under gravity, photons slam into it and push it back out. The result is not a universe of collapsing clouds, but a vibrating fluid. Pressure from radiation fights gravity, and the whole plasma rings with sound waves that sweep across space. To scientists, this is not just poetry. Those waves leave imprints, peaks where matter is slightly denser, troughs where it is slightly emptier, but nothing like a true void. No one expects a cavern hundreds of millions of light-years wide to emerge while photons are still trapped. The coupling is too strong, the pressure too high. Then, about 380,000 years after the Big Bang, the mission profile changes. The universe cools enough for electrons to bind to protons and form neutral atoms. Photons decouple, racing off through space as free radiation. That afterglow is what is detected today as the cosmic microwave background, a nearly uniform bath of microwaves filling the sky. By the end of tonight, you're going to understand why that uniformity is so shocking. When mapped with precision spacecraft, the CMB temperature only varies at the level of 1 part in 100,000. The early universe is astonishingly smooth. No one predicts, from that picture alone, the wild filamentary cosmic web seen now. Yet given billions of years, gravity amplifies every tiny excess. Overdensities pull in more matter, becoming galaxies, clusters, and sprawling superclusters. Underdensities lose matter to their surroundings and slowly evacuate, becoming the vast voids that lace the space beyond our local boundary. The local void, the KBC underdensity, and all the empty regions near the solar system are late-time products of this long, relentless evolution. So when the CMB shows a universe that looks nothing like our lumpy neighbourhood, that is not a contradiction. It is a before and after shot. The next step is to ask, if the starting conditions were so uniform, how unlikely is it that we ended up in one of the emptier rooms of the cosmic mansion? To see how dramatic that before and after really is, you have to look at the universe's baby picture. Not a photograph of galaxies and planets, but of light itself, the cosmic microwave background. Now, let's begin. The CMB is the afterglow of the Big Bang, stretched by cosmic expansion into faint microwave radiation that fills all of space. It was released about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral atoms. At that moment, the thick plasma fog cleared. The universe became transparent, and light that had been scattered at every turn was suddenly free to travel. That ancient light is still washing through the solar system right now. Satellites like COBE, WMAP, and Planck were built as precision thermometers to map it across the entire sky. They spin, scan, and slowly build a full sky image of the microwave glow, measuring temperature differences a few millionths of a degree. By the end of tonight, you're going to understand why those tiny differences matter so much for the lonely pocket we live in. The expectation was that the early universe should be smooth on large scales. The reality? It is almost unimaginably smooth. The CMB temperature is about 2.7 Kelvin everywhere, with variations only at the level of 1 part in 100,000. That means that if the average were the height of a 10-story building, the typical bump would be the thickness of a sheet of paper. No one expects a baby picture to be that flawless, but it is not perfectly flawless. Planck and its predecessors discovered a delicate mottling. Tiny hot and cold spots scattered across the sky. Those slightly hotter regions mark places where the plasma was a bit denser and the radiation a bit more energetic. The colder regions were a bit less dense. Over billions of years, gravity amplified those almost imperceptible differences, pulling matter into denser patches that became galaxies and clusters, and evacuating the regions in between into filaments and voids. So the same 1 in 100,000 ripples in the CMB that seeded the entire cosmic web also seeded the empty expanses we now call cosmic voids. The vast underdense regions around the Milky Way are late-time descendants of those cold spots. On the CMB map, they are barely visible as tiny temperature dimples. In the present-day universe, they can span hundreds of millions of light years. Here is the tension. The CMB says the early universe was astonishingly uniform. The large-scale sky today, averaged over enormous volumes, still respects that uniformity. But when you zoom in on our neighbourhood, the density drops. Our galaxy seems to live in or near an underdense bubble, while the CMB suggests no such special pocket at the beginning. How unusual is that? Are we sitting in a rare fluctuation, or exactly the kind of region you should expect once gravity has had 13.8 billion years to work? Tonight, we're going to push that question further and ask whether living in an emptier-than-average region can actually trick observers inside it about how fast the universe is expanding. To see whether an emptier pocket is a trick or a clue, you have to rewind the whole mission of the universe. Not to galaxies, not to planets, but to a time when space was so smooth that the densest and emptiest regions differed by only one part in 100,000. Now, let's begin. Imagine a nearly uniform fog of dark matter and gas filling all of space just after the Big Bang. Some patches are slightly denser, some slightly thinner. That's it. No grand cosmic web, no vast skeletal framework, just tiny numerical advantages written into the early universe. Gravity turns those tiny advantages into destiny. A region that's a little denser exerts a slightly stronger pull. It attracts more matter, which makes it denser still, which makes its gravity even stronger. Over millions, then billions of years, those tiny bumps grow into long filaments, massive clusters, and the knots where thousands of galaxies gather. Designed as small ripples in the cosmic microwave background, they become the backbone of the large-scale structure. But there is a complementary story. Where there is a winner, there must be a loser. Slight underdensities, the regions that start a little emptier, begin to lose the gravitational tug-of-war. Matter streams out of them toward those growing filaments and clusters. The result is counterintuitive. Emptier regions do not stay small. They expand, merge, and evacuate. They become the enormous cosmic voids that span tens to hundreds of millions of light years. By the end of tonight, you're going to understand why that process is not just an artistic metaphor. It is something scientists can watch unfold in numerical experiments. These are called n-body simulations. Take billions of dark matter particles, place them in a virtual cube of space with initial conditions drawn from the early universe power spectrum, then let gravity run. No one expects neat analytic formulas to capture all of this. The computer becomes the laboratory. In those simulations, Millennium, Illustris, and their successors, the same pattern appears again and again. Filaments thread the volume. Clusters blaze at the intersections. Between them, vast cavities open up where the particle density plummets. The cosmic web emerges not because the code was told to draw one, but because gravity plus the initial conditions almost forces it. And in those cavities you naturally find underdense regions that look a lot like the local void around our own Milky Way. The prediction is clear. If you drop observers almost anywhere in these simulated universes, many of them will live near the edge of a void, in a region that feels isolated, with fewer galaxies than the cosmic average. Living near a void is not inherently exotic. The real question, the one that starts to threaten our measurements of the expansion, is sharper. How big and how deep is our particular void compared to what these simulations say is typical? Because if our local underdensity is too extreme, then something far stranger than simple gravity might be shaping the boundary between our pocket and the rest of the cosmos. In the standard picture of the cosmos, our pocket is not an exception. It is part of a pattern. The large-scale universe looks like a vast three-dimensional web with bright filaments of galaxies and clusters separated by dark, mostly empty cavities. In lambda CDM cosmology, those cavities, cosmic voids, are not glitches. They are predictions. Gravity amplifies tiny ripples in the early universe. Regions that start a little denser pull in more matter and grow into clusters and superclusters. Regions that start a little emptier lose matter to their surroundings and grow into voids. Run this on a supercomputer, fill it with dark matter and expanding space, and scientists can count how many voids appear, how large they are, and how deep their underdensity becomes as the mission of structure formation unfolds. Now, let's begin to compare that theoretical map to our own neighbourhood. Surveys of nearby galaxies suggest the Milky Way sits near the edge of an underdense region hundreds of millions of light-years across, often labelled the KBC void. Its claimed depth is on the order of 20–50% less matter than the cosmic average, depending on how the boundary is drawn and which tracers are used. That is not a tiny fluctuation, that is a real dent in the cosmic web. So how rare is a KBC-like void in lambda CDM simulations? Tonight we're going to let the computers answer. When cosmologists search giant numerical universes for regions with the same size and depth, some studies find that such voids are uncommon but not impossible, maybe a few in 1,000 observer locations, depending on the exact criteria. Others, using different simulations or stricter definitions, argue that a void this extreme would be a serious outlier, something that almost never appears in a statistically fair sample. This is where expectation meets observation. The theory says voids are everywhere, with a smooth distribution of sizes and depths. The data say our inferred void might be sitting on the tail of that distribution, right where no one predicts a typical observer should land. No one expects to wake up in one of the emptiest large patches the model can generate, yet that is one way to read the numbers. But there is an important distinction. Living near a modest local void a few tens of megaparsecs across, slightly underdense, is common in simulations. Plenty of Milky Way-like galaxies end up in such environments. Living inside an enormous, very deep underdensity that could single-handedly resolve the Hubble tension is a different claim. That requires a bubble so large and so empty that it starts to push the limits of what lambda CDM usually produces. By the end of tonight, you're going to understand why this matters for the expansion rate. For now, hold on to this. Our pocket may be somewhat special, but probably not uniquely so. That opens the door to a more unsettling possibility. What if observers are more likely to arise in slightly unusual regions? What if there is a selection effect hiding in the way life, planets, and measuring instruments populate the cosmic web, quietly biasing what we think the universe looks like beyond our local boundary? So, now, the question sharpens. If life, planets, and instruments might prefer slightly weird neighborhoods, does that mean the universe broke its own rule about being the same everywhere on large scales? That rule has a name, the cosmological principle. It says that on sufficiently large scales, the universe is statistically homogeneous and isotropic. Not perfectly smooth, not identical in every direction, but when you average over enough space, the same cosmic recipe shows up almost everywhere. Tonight, we're going to push on that promise and see how far it can bend before it breaks. On small scales, the universe is a mess. Galaxies collide. Clusters form knots. Voids open up like great, dark caverns in the cosmic web. No one predicts a smooth, uniform sea of galaxies when zooming in to the scale of individual clusters or superclusters. The principle only claims that if you keep zooming out past the local chaos, the big picture settles down. So what counts as large enough? Observations from galaxy redshift surveys, from the Sloan Digital Sky Survey to more recent missions, suggest a threshold. Once the view spans regions roughly 300 million light-years across and beyond, the universe's properties start to average out. The number of galaxies, their types, their motions, the distribution of matter and dark matter, region to region, they look statistically the same. Think of it like flying over an ocean. Up close there are waves, foam, and swirling currents. From a low-flying aircraft, the surface looks wildly structured. But from orbit, those details blur into a single, nearly uniform blue. Voids, filaments, and clusters are the waves. The large-scale homogeneity is the ocean itself. The KBC scale underdensity, the idea that our solar system sits in a bubble hundreds of millions of light-years wide that is slightly emptier than average, lives right on the edge of that transition. That makes it dangerous territory for the cosmological principle. If the underdensity were too deep, too wide, or too precisely centered on our position, it would do more than color local measurements. It would start to mimic cosmic acceleration or distort the inferred expansion rate in ways that contradict what is seen in the cosmic microwave background. By the end of tonight, you're going to understand why most scientists think that hasn't happened. Current data suggest our local void is a modest dip, not a catastrophic hole, large but not unique, uncomfortable but still within the statistical wiggle room allowed by a universe built from random quantum fluctuations stretched by inflation. So the cosmological principle likely keeps its promise. The universe on the largest scales still looks like one grand, statistically uniform system. But where we sit inside that system in a slightly underdense pocket may quietly bias how we read its signals. Now, let's begin to ask a harder question. If the principle holds, why does the universe's expansion still refuse to line up with our best models? If the universe is one grand, statistically uniform system, why does our particular pocket seem to bend the rules? To answer that, there's a quiet assumption in cosmology that has to be dragged into the light. The idea that we are typical observers living in a perfectly average spot. Tonight, we're going to question that assumption. Cosmologists often treat every observer as interchangeable. Pick a galaxy at random, drop a spacecraft there, and the large-scale universe should look the same. But the cosmic web is not featureless. It's a tangled structure of dense clusters, slender filaments, and vast voids where almost no galaxies live. Our solar system orbits inside the Milky Way, which itself sits near the edge of an underdense region called the local void. That address matters. It can quietly bias what scientists think they've discovered about space beyond. Before we get started on equations, imagine something closer to home. One person grows up in the heart of a crowded city, another lives in a tiny rural town. Each is asked to estimate the average human population density on Earth, using only what they see around them. The city dweller points to skyscrapers and packed trains. The rural observer looks at empty fields and long, quiet roads. Both are honest, both are wrong in different directions. The truth only appears when many such local measurements are combined and corrected for where each observer lives. Our galaxy faces a similar problem. If you live near a void boundary, the surrounding galaxies are not arranged like they would be in a truly average patch of the cosmic web. Gravity pulls galaxies out of the void and toward denser filaments, creating coherent flows. That motion can subtly distort how fast they appear to recede. Type Ia supernovae, used as standard candles, might look slightly closer or farther than they would from a more typical vantage point. From here, the inferred expansion rate can shift, which feeds directly into debates like the Hubble tension. This is where cosmic variance enters. Even in a universe that is uniform in the statistical sense, different regions will, by pure chance, have slightly different local densities, velocities, and histories. No one predicts every patch to match the cosmic mean exactly. Instead, there is a spread, a natural randomness in which some zones are a bit emptier, some a bit richer, some with faster local flows, some slower. Our measurements ride on top of that randomness. By the end of tonight, you're going to understand why this raises a deeper question. Are we truly typical observers? Just one random galaxy in an ordinary filament, or are we selected to live in a somewhat special pocket, because that's where galaxies, heavy elements, and eventually life can form? No one expects the answer to be comforting, because if our address is biased by the very fact that we exist, then every reading of the universe's expansion may carry a hidden anthropic fingerprint that the next section will press on very hard. If our address might be biased, then the next move is uncomfortable but unavoidable. Learn to think anthropically. Now, let's begin. Anthropic reasoning sounds exotic, but at its core it just says this: any observation you make is already filtered by the fact that you exist to make it. That filter is powerful. It quietly edits what you are likely to see in space long before any telescope ever turns on. Before we get started, notice how this plays out in simple, familiar ways. Out of all the stars in the Milky Way, you do not wake up around a red giant about to shed its outer layers. You find yourself orbiting a long-lived, relatively stable star in a calm phase of its evolution. That is not an accident. Short-lived or wildly unstable stars do not give planets billions of years to cool, form oceans, and assemble chemistry into biology. Observers appear where there is time to evolve. Scale that up. Out of all possible universes with different physical constants, you do not open your eyes in a cosmos where gravity is so strong that everything collapses into black holes, or so weak that no galaxies condense at all. You find yourself in a solar system where chemistry, planets, and galaxies are possible, because only in that narrow band of constants can a mission, a spacecraft, or a scientist ever exist to wonder about them. No one predicts observers in a universe with no stable atoms. Now apply this to the cosmic web itself. Galaxies are not sprinkled randomly. They ride along filaments of dark matter, feeding on cold gas and heavy elements. Life is more likely to arise where previous generations of stars have exploded, seeding space with carbon, oxygen, iron, and all the ingredients of rocky planets and complex molecules. It also prefers environments that are quiet enough for long, stable eras, yet connected enough to keep recycling material. That combination points to very specific real estate. Cluster cores are rich in galaxies and metals, but they are also violent. Intense radiation, frequent interactions, and turbulent gas that can strip atmospheres and tear solar systems apart over cosmic time. Deep in voids, the opposite problem appears. Extreme isolation, fewer heavy elements, and fewer chances to assemble complex planetary systems at all. So picture a sweet spot, near the edge of a void where a filament threads past. connected to the larger web, but not overwhelmed by its loudest neighbourhoods. Enough heavy elements for planets, enough nearby galaxies to keep the ecosystem of gas and dust alive, but with gravitational tides and radiation fields that are relatively gentle. The Milky Way's location on a filament skirting the local void fits that description suspiciously well. Here the pattern interrupt lands. Perhaps our isolated pocket is not a bizarre cosmic accident. Perhaps it is a selection effect. By the end of tonight, you're going to understand that of course observers tend to find themselves in regions where observers can exist. The real tension is this. If anthropic reasoning explains our nice pocket, does it also mean our measurements of the universe beyond are systematically skewed? That is the boundary the next section will press against very hard. So if our nice pocket is not an accident, what kind of neighbourhood are we actually in? Are we in the cosmic equivalent of downtown Manhattan, or are we living in a quiet suburb on the edge of a vast, dark field? Now, let's begin. Dense galaxy clusters sound glamorous. Thousands of galaxies packed into a region only a few million light-years across. Immense clouds of hot gas. Enormous dark matter halos. But for a galaxy trying to build planets and keep them stable, these regions can be brutal. Frequent, close encounters twist galaxies with strong tidal forces, flinging stars into long, tidal tails. The intracluster gas is heated to tens of millions of degrees, forming an X-ray bright atmosphere that can ram pressure strip cooler gas right out of a galaxy's disk. In that environment, the raw material for stars is peeled away like paint in a sandstorm. Spiral galaxies get harassed into smooth, gas-poor ellipticals. Star formation can shut down early. No one expects gentle, billion-year-long eras of quiet disk evolution in the very core of a rich cluster. The space there is crowded, noisy, and constantly rearranged by gravity. Near a void, the picture shifts. The cosmic web thins out. Galaxies are more isolated, with fewer high-speed collisions and less hot intracluster wind. Their cold gas can linger for much longer, feeding star formation across extended timescales. Surveys of the large-scale structure show that galaxies in the deepest voids often look small, blue, and relatively pristine, as if the main story of the universe has been happening somewhere else. But there is a twist. Those truly extreme void galaxies tend to have lower star formation rates and fewer heavy elements. They evolve more quietly, yet also more slowly. With fewer past generations of massive stars to enrich their gas, they may be short on the carbon, oxygen, silicon, and iron that rocky planets and complex chemistry depend on. Stable? Yes. Fertile? Maybe not. That sets up an intriguing possibility for the local group. The Milky Way and Andromeda do not live in the blazing heart of a cluster, but they are not drifting in the emptiest part of a void either. Observations suggest this region sits near the boundary of an underdense zone, sometimes called the local void or KBC void, while still connecting to filaments that feed in gas and smaller galaxies. So the local group might be in a sweet spot, close enough to denser regions to inherit a rich supply of heavy elements and occasional interactions, but far enough from the crowded cores that the solar system can orbit quietly for billions of years without catastrophic disruption. No one predicts this exact balance in advance. It is discovered after the fact, when scientists map the surrounding cosmic web and realize how delicately positioned our galaxy seems to be. From an anthropic perspective, That matters. If habitable galaxies prefer these in-between environments, edges of voids, outskirts of filaments not too hot, not too empty, then observers will often measure a universe where their immediate neighbourhood looks like an isolated pocket compared to the grand average. By the end of tonight, you're going to understand that this is not a coincidence. It is a selection effect, written into the large-scale structure of space itself. But if our vantage point is special, the next question is sharper. How much does that special vantage distort what we think the rest of the universe is doing beyond our local boundary? So if our vantage point can distort the story, the next move is obvious. Map the stage we're standing on. Tonight, we're going to watch scientists turn the sky from a flat wallpaper of galaxies into a three-dimensional flow field, showing exactly how matter is streaming through space around the Milky Way. Now, let's begin with one of the quiet revolutions in modern cosmology, projects like cosmic flows. On the surface, it looks simple. Measure how far away nearby galaxies are, measure how fast they're moving, then plot them in 3D. In practice, it's a precision mission. Distances come from standard candles like Type Ia supernovae and from scaling relations between a galaxy's rotation speed and its luminosity. Velocities come from tiny shifts in spectral lines riding on top of the general expansion of the universe. That expansion is the key reference. In a perfectly smooth universe, every galaxy's speed would follow a pure Hubble law. Velocity equals Hubble, constant times distance. But that's not what is observed. Some galaxies move faster than Hubble's prediction, some slower, some even sideways relative to the pure radial flow. Those deviations are called peculiar velocities. They are the fingerprints of the cosmic web written into the motion of entire galaxy systems. Peculiar velocities tell you where gravity is winning. Matter flows toward overdensities and away from voids, like a slow-motion, three-dimensional wind. Trace enough of those flows, and the invisible landscape appears. No one predicts that by charting tens of thousands of galaxy motions, a single, coherent basin of attraction would emerge, swallowing familiar landmarks like the Virgo cluster. That basin is Laniakea. Using cosmic flows data, researchers reconstructed streamlines of galaxy motion and found that the Virgo cluster, the Hydra, Centaurus region, and many others all drain into one extended gravitational domain. The Milky Way is just one small river in this continental-scale watershed of about 100,000 galaxies stretching over 500 million light-years. Our solar system orbits inside a galaxy that is itself drifting along these flows, sliding down the gentle slope of Laniakea's potential. But the same reconstructions reveal something else. An emptiness. When the density field is inferred from those velocities, the local group appears near the edge of a large, underdense region, the local void. Galaxy flows around us stream away from this hollow and toward denser attractors like Virgo and the Great Attractor region. Expectation. A typical average patch of the cosmic web. Reality. A boundary zone with one side pulled by clusters and the other opening onto a vast, underfilled pocket. Before we get started on what that means for measurements of cosmic expansion, notice the pattern. This picture of living on the boundary of an isolated pocket is not a hand-waving idea. It is carved out of data, redshifts, distances, peculiar velocities, all woven into increasingly detailed 3D maps of our neighbourhood. The mystery now is not whether that pocket exists, but whether its presence is quietly biasing every number used to describe the universe beyond our local boundary. So here is the pattern interrupt. Up to now, the picture has been conservative. A modest pocket, a gentle underdensity, a small correction on top of a homogeneous universe. But what if that whole framework is wrong? What if the entire observable region is not truly uniform on large scales, and our solar system is sitting inside a gigantic cosmic hole that rewrites cosmology from the ground up? Tonight, we're going to briefly step into that more radical universe. In this version, the Milky Way does not just live near a local void, it sits almost exactly at the centre of a vast underdense region spanning hundreds of millions of light years. Space around us would be emptier than average in every direction. And that emptiness would not just be scenery, it would change how the expansion of the universe is inferred from the motion of galaxies. Now, let's begin with the models that tried to make this precise. In the late 20th century, scientists developed what are called Lemaitre, Tolman, Bondi, or LTB models. Instead of assuming the same density everywhere, these models describe a spherically symmetric universe where density can vary with radius. Put an observer at the center of a huge underdensity. Let the outer regions be denser, and something strange happens. The light from distant galaxies can look as if cosmic expansion is accelerating, even if there is no dark energy at all. No one expects that at first glance. The standard mission is clear. Use supernovae to track how fast space expands with time, discover that the expansion speeds up, and invoke dark energy to explain it. But in an LTB universe, the same supernova data could be reinterpreted as a geometric illusion. The boundary between our void and the denser outer regions would create a gradient in expansion rate. From our vantage point, galaxies beyond that boundary would appear to accelerate away, not because a mysterious energy fills the cosmos, but because we live in a very special place. It sounds elegant, it uses general relativity, it uses real observables, and absolutely no one anticipates how severely the data will push back. To make this work, the solar system has to sit implausibly close to the exact center of the void, or else the sky would look lopsided. The cosmic microwave background would carry a huge dipole signal from our off-center motion. The detailed pattern of temperature fluctuations would be distorted, precision measurements of the CMB, galaxy clustering, and baryon acoustic oscillations all pile on. The triad is brutal. The required void is too big, too deep, and too centered on us. By the end of tonight, you're going to understand why most cosmologists now treat these extreme "we live in a special bubble" models as ruled out, at least in their purest form. The universe on the very largest scales really does look homogeneous and isotropic to extraordinary precision, but that does not rescue us from the more subtle problem. A moderate local underdensity still exists. It still changes the flow of galaxies, the local value of the Hubble constant, the way the cosmic web feeds matter into our region of space. The next step is to see how that quieter, more believable pocket can still bias precision cosmology, even when the rest of the universe plays by the standard rules. A quiet local pocket sounds harmless, but how far out does that pocket really reach before the rest of the universe drowns it out and forces everything to average together? Now, let's begin with scale. Cosmologists think in megaparsecs. 1 megaparsec is about 3.26 million light-years. On very local scales, tens of megaparsecs, you are deep inside the quirks of the cosmic web. Here, individual filaments, clusters, and voids dominate. The local group, the Virgo cluster, the local void, these aren't background noise, they are the landscape. Push out to intermediate scales, hundreds of megaparsecs, and the picture starts to smooth. You still see filaments and gaps, but each survey volume contains many separate regions, many little universes within the universe. Go farther still, to gigaparsec scales, and something remarkable happens. The clumpiness washes out. The universe begins to look statistically homogeneous, the same in every direction, the same from place to place. Tonight, we're going to use that hierarchy of scales to understand when our bubble matters and when it doesn't. On the smallest ranges within a few tens of megaparsecs, local flows dominate the apparent expansion. Galaxies fall toward clusters, get pushed out of voids, feel the gravitational wind of nearby overdensities. Try to measure the Hubble constant here, and the motion from structure can be as large as the motion from global expansion. Extend to a few hundred megaparsecs, the scale of the proposed KBC void, and the underdensity still leaves fingerprints. Supernova surveys that rely heavily on galaxies within this range can be biased. The local underdensity makes galaxies recede a bit faster than average, nudging the inferred expansion rate upward. No one expects a perfectly fair sample of the cosmos if the sample never really escapes our own low-density basin, but surveys that reach a higher redshift, out to billions of light years, start to break free. Each distant supernova, each galaxy at Z01 1 or beyond lives in a different patch of the cosmic web. The mission design here is statistical. Observe so many independent regions that any one void, any one overdensity, becomes just one term in a vast average. By the end of tonight, you're going to understand why this is the only way to test whether our pocket is a trick or a clue. At the largest scales, the cosmic microwave background sits in a category of its own. Those photons come from a shell about 14 gigaparsecs away, spanning the entire observable universe. The CMB doesn't care about a single void a few hundred megaparsecs wide. It averages over everything. All the planets, all the galaxies, all the solar systems, all the empty space between. So, the isolated pocket matters. It sharpens local tensions, bends nearby measurements, and challenges how spacecraft, telescopes, and scientists interpret the expansion right around us. But it does not overturn the global picture. A universe that, beyond our boundaries, still expands smoothly, still looks nearly homogeneous, and still obeys the same underlying rules of cosmic evolution. The real question is not whether our bubble exists. It's how far its influence can reach into the deepest, most precise measurements we make of the universe itself. So here is where the mystery sharpens. Our bubble isn't just a curiosity in the map of galaxies, it sits right in the crosshairs of one of the biggest tensions in modern cosmology: how fast the universe is expanding right now. Before we get started, put two numbers in your head. Local measurements using supernovae and Cepheid variables in nearby galaxies keep landing around 73 to 74 kilometers per second per megaparsec. That means every megaparsec of space expands with an extra 74 kilometer lengths of recessional speed. But when scientists read the cosmic microwave background with the Planck spacecraft and evolve that early universe snapshot forward using the standard model, they get 67 to 68. Same universe, two methods, a gap of roughly 9%. Tonight, we're going to put our void under the microscope and ask how much of that 9% can an underdense pocket really explain? In a universe where the cosmic web is full of voids and filaments, no one expects perfect uniformity on small scales. An underdensity means weaker gravity locally, so space in that region can expand a little faster than average. The question is not whether this effect exists, it's how big it can get without breaking everything else we've discovered. Models that embed a KBC-like void inside an otherwise standard cosmology try to answer exactly that. They take a region perhaps 200 to 300 megaparsecs across, dial its density down by 20–50%, and compute what an observer inside would infer for the Hubble constant. The result is striking, but constrained. In many of these simulations, the inferred Hubble rate ticks upward by a few percent, sometimes 2, 3, occasionally nudging toward 5 in aggressive scenarios. Contrast that with the tension. To drag 67, 68, all the way up to 73, 74, the local expansion would need to be biased by nearly the full 9%. For that to come purely from a void, the underdensity would have to be deeper or larger than what galaxy surveys actually see around the solar system. No one predicts a giant, perfectly spherical, nearly empty hole centered exactly on the Milky Way. And absolutely no one anticipates such a feature without leaving other signatures in the cosmic microwave background and large-scale flows of galaxies. So most analyses converge on an uncomfortable middle ground. A realistic void can shift the local Hubble constant. But only part way. It can soften the tension, not erase it. By the end of tonight, you're going to understand that our isolated pocket is not the villain or the hero. It's a supporting character in a larger cosmic drama that might involve new physics, hidden systematics, in our distance ladder, or both. Now, let's begin to ask the sharper question. If our local underdensity is only half the answer, what else is the universe trying to tell us through this stubborn, persistent Hubble tension? And where should we look next to hear it more clearly? So, if our local underdensity is only half the answer, what's lurking in the other half of the Hubble tension? When the universe refuses to match the numbers, scientists do something dramatic. They widen the suspect list. Before we get started, remember what's at stake. The Hubble constant is not just a speedometer for space, it is a control knob for the entire cosmic story, from the age of the universe to the fate of distant planets and galaxies. When nearby supernovae say the expansion is faster and the cosmic microwave background says it is slower, that is not a tiny bookkeeping error. That is a flashing red boundary where theory and observation collide. One possibility is that the laws themselves are incomplete. Some missions in theory space point to early dark energy, an extra burst of repulsive energy active only in the young universe just before the CMB was imprinted. Others propose extra relativistic species, sometimes nicknamed dark radiation, that would have streamed through the solar system and beyond, subtly changing how the early plasma cooled. Still others let dark energy evolve with time, so the equation of state that accelerates the universe today was not the same billions of years ago. Change the energy recipe in the early universe and the CMB inferred Hubble constant shifts. But there is a more down-to-earth suspect. Us. Or rather, our measurements. Distance ladders rely on calibrating one rung of the cosmic system against the next, parallax to Cepheids, Cepheids to supernovae, supernovae to far-flung galaxies. Tiny biases in how those standard candles are selected, dust-corrected or standardized can echo across billions of light years. On the other side, CMB analyses depend on foreground subtraction, beam calibrations, and complex statistical pipelines. No one expects those pipelines to be perfect. No one predicts that dozens of independent teams will make identical choices. So hidden systematics remain a live, serious possibility. That is where our local environment comes back in. Local underdensity, bulk flows and peculiar velocities are part of the mundane foreground that must be stripped away. Our void is not an exotic new force. It is more like the solar wind of cosmology, a messy, local medium that every spacecraft of measurement has to push through before seeing the pristine, intergalactic space beyond. Quantify that properly and some of the tension melts. Ignore it, and the numbers lie. Pattern interrupt. What if the void explanation is not a rival to new physics at all, but a filter? Even if it cannot fully erase the discrepancy, correcting for our underdense pocket sharpens the remaining mismatch. The residual tension, if it survives every local and instrumental bias, becomes a cleaner, louder signal that the universe is genuinely stranger than the standard model predicts. By the end of tonight, you're going to understand that this is not a failure of cosmology. It is the method. Science advances by exhausting the boring explanations first. Every time a bias is ruled out, including the bias of living in an isolated pocket of the cosmic web, the case for truly new physics either weakens or grows stronger, but it always becomes clearer. Now, let's begin to follow that logic to its extreme. What if, after clearing away voids, winds, and systematics, the tension is still there? If our pocket of space is unusual, the real test is simple. Do distant galaxies agree with our story, or are they living under a completely different set of rules? Tonight, we're going to push past our local bubble and ask the rest of the universe what it thinks. Before we get started, zoom the mental camera way out. Nearby, measurements of expansion and density are taken within a few 100 million light years. That's the regime where the local void, the KBC underdensity, and all the messy details of our immediate cosmic neighbourhood still matter. But deep redshift surveys reach much farther. They map galaxies out to billions of light years, sampling dozens, even hundreds, of independent cosmic volumes far beyond the influence of our particular patch. The strategy is elegant. Measure how many galaxies live in a given volume, how strongly they cluster, how big the voids are, and how fast the expansion appears at different redshifts. Then compare those statistics from one region to another and from the nearby universe to the distant one. If our region were wildly atypical, if the Milky Way were truly marooned in an isolated pocket, systematic differences should jump out. The expansion rate inferred from close-by supernovae should refuse to match the one inferred from galaxies billions of light years away. The size and distribution of voids should drift, hinting that the cosmic web itself changes character with distance. That's the expectation. Reality is more stubborn. Surveys like SDSS, DES, and others have traced a three-dimensional map of the cosmic web on scales of hundreds and even thousands of megaparsecs. They see filaments of galaxies, clusters where the web knots up, and enormous voids where the density drops. The exact pattern is chaotic, but the statistics are not. On scales larger than a few hundred megaparsecs, the galaxy clustering, the void sizes, and the way structures grow with redshift line up with standard cosmology and the cosmological principle. No one expects perfect uniformity on small scales. There are rich clusters, thin filaments, and yawning gaps. But when the data are averaged over sufficiently large regions, every surveyed patch looks, statistically, like every other surveyed patch. No one predicts that the universe will be this cooperative, and absolutely no one anticipates how cleanly the numbers fall into place once the averaging is done. This agreement is a powerful clue. It suggests that our local underdensity is a regional quirk of the cosmic web, not a sign that the universe fractures into fundamentally different domains with incompatible expansion laws. The same underlying rules seem to govern space near and far, they just express themselves through different local arrangements of matter. By the end of tonight, you're going to understand why that matters for the Hubble tension. Because if distant galaxies agree on the big picture, yet the numbers still don't line up, the explanation may have to reach beyond local bubbles and into the physics of the universe itself. If the numbers might be pointing beyond local bubbles, the next question is brutal and precise. Could a universe like ours naturally build a pocket like this in the first place? To answer, scientists do something audacious. They recreate the entire cosmos inside a computer and then go looking for neighbourhoods that feel eerily familiar. Now, let's begin. Imagine a digital cube of space, hundreds of millions of light years on a side. Inside it, a supercomputer tracks billions of dark matter particles and gas elements, evolving them from the smooth, hot plasma after the Big Bang to a tangled web of filaments, clusters, and voids. Gravity pulls, gas cools, stars ignite, and tiny numerical ripples grow into something that looks uncannily like the real cosmic web. These are not toy models, they're full-scale missions in silicon with names like Illustries, Eagle, and Millennium, each one an artificial universe that can be paused, rewound, and fast-forwarded. By the end of tonight, you're going to understand why that control is so powerful, because in a simulation, no galaxy is too far, no region too faint, and no observer too hypothetical. Inside these digital universes, researchers start hunting. They search for Milky Way analogues, spiral galaxies with similar mass, quiet merger histories, and a modest swarm of satellites. Then they look for pairs that resemble the local group, with a Milky Way-like galaxy and an Andromeda-like companion orbiting in a shared dark matter halo. Not too close, not too far. Around those, they map the surrounding density field, asking, does this simulated local group sit near the boundary of a void, the way ours seems to sit near the local void or a KBC-like underdensity? The surprising part is not that they find some analogues, it's how detailed the match can be. In several lambda CDM simulations, scientists have located Milky Way, like galaxies perched on the edge of large voids, with density contrasts similar to the inferred 20–30% underdensity around us. The local flow of galaxies in those regions shows the same pattern. Matter streaming out of emptier zones, drifting along filaments toward more massive clusters, like a slow, gravitational wind sculpting the landscape. No one expects every run to produce a perfect copy of our address. No one predicts that our exact configuration is common, but absolutely no one anticipates that it would require exotic new physics just to exist. The current picture is subtler. In lambda CDM, pockets like ours are unusual but not absurd, rare but not forbidden. And that leaves room for a critical twist. Because once a simulated universe contains a few Milky Ways in void rims, scientists can perform the ultimate what-if experiment. They can drop virtual observers into different locations, deep inside a void in the middle of a rich cluster, or on a quiet filament like ours, and ask what cosmology each observer would infer from supernova, galaxy surveys, and the cosmic microwave background. Same underlying universe, different apparent expansion rates, different local Hubble tensions. The real question is, when those digital observers start disagreeing, how far can their answers drift before the illusion of a single, simple universe breaks? Now, let's begin with a different kind of observer. Up to now, you've been standing near the edge of a void, watching a relatively lonely sky. Tonight, we're going to move you. Imagine an advanced civilization that evolved deep inside a rich galaxy cluster, the kind of environment where gravity never lets go. Thousands of galaxies crowd their sky. Giant ellipticals, spirals, dwarfs, all packed into a volume that would hold only a few galaxies in our region. For them, close encounters are routine. Galaxy mergers aren't rare cosmic accidents, they're part of the weather. Tidal tails arc across the cluster like frozen rivers of stars. Peculiar velocities, those extra motions on top of cosmic expansion, are huge, hundreds or even over 1,000 kilometers per second as galaxies orbit the cluster's center. To scientists there, the local gravitational field is intense, noisy, and ever-shifting. Now compare that to the quiet filament at the edge of a void where the Milky Way lives. Our nearest big neighbour, Andromeda, is millions of light-years away. Major mergers are events that happen once in billions of years, not in every epoch of recorded history. Our peculiar velocity is modest, and large parts of our sky point into relatively empty space. The same universe, completely different daily experience. Prediction versus observation becomes a trap here. Cluster astronomers measuring galaxy densities would infer a universe that feels crowded, dynamically hot, and strongly clustered. Their typical galaxy lives in a swarm. Their calibration of distance indicators might lean on galaxies buffeted by interactions, lit up by bursts of star formation, distorted by tidal forces. Our calibrations lean on calmer systems in a quieter flow. The bias tilts in opposite directions. From inside a massive cluster, the inferred average matter density of the cosmos might come out higher. Local measurements of the Hubble expansion could be dragged down by those large, peculiar velocities, making the cosmic expansion rate look slower than it truly is. From our underdense neighbourhood, the opposite can happen. Fewer gravitational tugs, cleaner recession velocities, a Hubble rate that looks a bit too fast. No one predicts that a single global expansion can look this different from two vantage points, until the data force the issue. Here's the pattern interrupt. Cosmology often talks about the average observer, but on small and intermediate scales that observer does not exist. Every vantage point lives somewhere on the cosmic web, in a cluster core, on a filament, at a void boundary, or deep in the emptiness beyond. Each position colours what the instruments on any future spacecraft will report. By the end of tonight, you're going to understand that our isolated pocket is not an error. It is a data point. To decode the true global behaviour of the universe, scientists have to reverse engineer those local quirks, ours, and the ones a cluster civilization would measure, until both stories fit into a single, shared cosmos. So, if our isolated pocket is just one data point, what checks that data point against the rest of the universe? In a mission full of local measurements and regional quirks, there is one signal that does not care where any particular galaxy ended up. It comes from a time before clusters, before voids, before anything that looks like the cosmic web you see in modern surveys. That signal is the cosmic microwave background. The CMB is not light from our neighbourhood or even from our half of the observable universe. It is fossil radiation from when the entire cosmos was a hot, dense plasma, about 380,000 years after the Big Bang, long before the Milky Way, the local void, or any recognisable isolated pocket existed. Tonight, we're going to use it as a control experiment the universe ran on itself. In that early plasma, tiny ripples in density were present, but the huge underdense regions we see now had not yet formed. There was no special cavity carved out for our solar system, no oversized void around our cluster of planets. The CMB shows that young universe as astonishingly smooth. Temperature variations are only about 1 part in 100,000. Those faint fluctuations are the seeds from which every later galaxy, filament, and empty region grew. Because the CMB is so uniform and because its tiny hot and cold spots follow a precise power spectrum across the sky, scientists can reverse engineer the global geometry and contents of space. The pattern of peaks and troughs pins down the overall curvature to be very close to flat. The mix of dark matter, normal matter, and dark energy, and the broad expansion history from the Big Bang to far beyond the present solar age. No one expects that level of precision from a fog of microwave photons, but that is what was discovered. Now, let's begin to test our void ideas against that backdrop. If the universe near us were dramatically underdense on truly gigantic scales, it would not just tweak local galaxy flows. It would bend the paths and energies of CMB photons as they cross that region. This shows up through the integrated Sachs-Wolf effect as photons climb in and out of evolving gravitational wells and hills. They gain or lose a tiny bit of energy. Extreme void models designed to fully fix the Hubble tension predict strong, distinctive ISW signatures and other distortions in the CMB sky. Those signatures are not seen. Prediction versus observation breaks. The boundary conditions written in the CMB refuse to cooperate with a universe where our pocket is an entirely different regime. So the CMB delivers a clear message. Whatever local wind patterns we sit in, whatever underdensity surrounds our spacecraft and galaxies, the universe on the very largest scales still behaves like a simple, nearly homogeneous system. Our isolated pocket can be a real perturbation, maybe even an important one, for what we measure. But it has to ride on top of that global solution, not replace it. By the end of tonight, you're going to understand that the rules written in the microwave sky apply here in our quiet bubble just as much as they do in the densest clusters beyond our horizon. So the global rules are written in that ancient microwave light. But inside those rules, not every neighbourhood plays the same game. And that raises a sharper question. Does the particular pocket our solar system lives in actually matter for life, or just for the measurements scientists make with telescopes? Now, let's begin with something concrete. Galaxies do not all grow up in the same kind of space. A galaxy buried deep inside a rich cluster lives in a crowded city of thousands of neighbours, bathed in hot plasma and hard radiation. A galaxy adrift in a vast void sits in a cosmic countryside with only a few lonely companions and a much thinner cosmic wind of infalling matter. Those environments change how stars form, how long they burn, and what they leave behind. Star formation histories and metallicity are the first big levers. Heavy elements, everything beyond hydrogen and helium, are forged in stars and detonated into space by supernovae, and sometimes by neutron star mergers. In dense filaments and cluster cores, generations of stars live and die quickly, enriching the gas with carbon, oxygen, silicon, iron. That means planets with rocky surfaces, complex chemistry, and potential biospheres can appear earlier in cosmic time. In the deepest voids, structure forms more slowly, galaxies are smaller and rarer, and enrichment can lag by billions of years. Before we get started on anthropic conclusions, notice the pattern. Too few heavy elements, and planets like Earth may be rare or delayed. Too many violent events, and planets may never stay stable long enough. The same supernovae that seed life with metals can also sterilize it if they explode too close. Gamma-ray bursts, focused beams of lethal radiation, are more common in low metallicity galaxies and in certain star-forming regions. Placement inside the cosmic web changes the odds of one of those going off in the wrong part of the sky at the wrong time. Cluster cores push this to an extreme. There, galaxies slam past each other, tidal forces tear at stellar systems, and the intra-cluster medium glows in X-rays. Planetary orbits can be disturbed by close stellar encounters. The background radiation is higher, the rate of nearby supernovae can spike. Designed for long, quiet epochs of chemistry and climate, fragile biospheres may struggle in that kind of gravitational and radiative crossfire. By contrast, a galaxy marooned far inside a huge void might be safe but starved. Fewer mergers, less gas inflow, slower growth, and lower metallicity could mean that for much of cosmic history, there simply are not enough heavy elements to build many Earth-like planets. Life is protected from chaos, but it may also be prevented from ever starting. Tonight, we're going to frame our location as a possible middle ground. The Milky Way seems to sit on a filament edge bordering the local void, not in the densest cluster, not in the emptiest abyss. Enough past star formation to enrich our planets, enough distance from cluster violence to keep our orbits calm, a candidate Goldilocks niche on the cosmic web. No one expects that to be a coincidence, but absolutely no one anticipates that this idea is settled either. The data are thin, the models are young, and the real test is still ahead. Comparing our quiet bubble to other pockets where life might have taken a different path or never emerged at all. So now the puzzle gets even stranger. It is not just that our solar system sits in a quiet bubble on the cosmic web. It is that every conclusion about the entire universe is being drawn from inside that one bubble at one cosmic moment along one narrow light cone. Tonight, we're going to push that to its limit. Imagine trying to understand an entire ocean while floating in a single tiny bay at a single tide level, with waves only reaching you from one direction. That is what cosmologists are doing in space. Light has a finite speed, so everything observed is not only far away in distance, but far away in time. Galaxies at different redshifts are not different places in one snapshot. They are different frames in a very long movie. Now, let's begin. The universe could, in principle, look very different just beyond the horizon of that movie. No one predicts that a single vantage point can directly sample every environment, every void, every cluster. Instead, scientists try to reconstruct a view from nowhere using an armory of indirect strategies. They build enormous simulations of structure formation evolving dark matter and gas from the smooth, nearly featureless cosmic microwave background into the tangled filaments and voids mapped today. They also lean on multiple independent probes that do not share the same local biases. The CMB gives a snapshot of the early universe that is uniform to one part in 100,000, a clean baseline, before our local void ever existed. Type Ia supernovae. Trace how cosmic expansion has changed over billions of years. Baryon acoustic oscillations leave a standard ruler in the clustering of galaxies. Gravitational lensing reveals how mass is actually distributed, regardless of how bright the planets or stars are. By the end of tonight, you're going to understand that the mission is not to pretend our pocket does not matter. It is to measure how much it matters. The same local underdensity that might skew the Hubble constant is not an embarrassment. It is a calibration tool. By modelling our void, subtracting its gravitational pull and its peculiar velocities, scientists try to turn a biased local reading of the cosmic wind into a more universal inference about the global expansion. Pattern interrupt. What if some bias can never be removed? There is a name for that. Cosmic variance. Even with perfect instruments, there is only one observable universe, only one realization of the random initial conditions that seeded the cosmic web. No one expects those statistical bumps to vanish entirely, so the question becomes unavoidable. In a universe where every observer is embedded somewhere, how close can any spacecraft, any survey, ever come to knowing what the cosmos looks like, on average, beyond its own horizon? So, when every observer is locked inside one realization of the cosmic web, the obvious question becomes dangerous. Are we in a boringly average part of space, or perched in an unusually quiet pocket that bends our view of the universe beyond? Tonight, we're going to press on that word typical until it starts to crack. Now, let's begin. In lambda CDM simulations, scientists let dark matter and gas evolve from almost perfectly smooth initial conditions into a tangled web of filaments, clusters, and voids. When those virtual universes are sampled the way a real galaxy survey samples ours, something striking appears. Regions like the Milky Way's neighbourhood on the edge of a modest void, laced into a filament, with a few nearby groups and no giant cluster dominating the sky, show up again and again. Not dominant, not rare, just one of many mid-density crossroads where a spiral galaxy and its planets can quietly orbit. That picture changes when the KBC scale void claims enter. Some reconstructions of local galaxy flows suggest an underdensity stretching hundreds of millions of light-years, big enough to nudge the measured expansion rate and maybe ease the Hubble tension. In simulations, voids that deep and that wide do appear, but not often. They live in the statistical tail, not the middle of the distribution. No one predicts that every observer will sit near the center of a vast bubble that happens to explain all their cosmological headaches at once. This is where typical in cosmology stops feeling intuitive. A galaxy can live in the low-density tail locally, while still being absolutely ordinary in other ways. The Milky Way's mass is close to the median for star-forming spirals. Its star formation history is unremarkable. Its central black hole is not extreme. In one histogram, local matter density, we might be a mild outlier. In another, galaxy properties, we sit right in the thick of the curve. Typical is not a single label, it is a whole row of overlapping bell curves. From an anthropic perspective, the target shifts again. Observers do not randomly sample all of space. They arise in rare pockets where heavy elements exist, where planets can form, where the radiation environment is stable for billions of years. By the end of tonight, you're going to understand why that selection effect quietly biases every view of the cosmos. Among all possible locations in the universe, habitable regions are already special. Among those habitable regions, our environment may be completely typical. So the emerging picture is nuanced. We are probably not at the geometric center of a 1 in a million KBC style void that rewrites the expansion history. But we are also not sitting in a perfectly generic patch of the cosmic web. We occupy a subtly biased, observer-friendly pocket, slightly underdense, gently connected to filaments, quiet enough for a long-lived solar system to notice the wider universe and to ask whether the view from here is the rule or the exception that proves it. So what does it actually mean to live in a pocket of the universe? It sounds like there should be a wall, a shell, some clean edge where our region ends and the rest of cosmic space begins. But as every mission that has chased a boundary has discovered, nature almost never draws hard lines. Before we get started on voids and filaments, go back to the edge of the solar system. For decades, textbooks casually mentioned the edge as if there were one surface where the sun's influence stops and interstellar space begins. Then Voyager showed up and turned that simple picture into a layered, dynamic frontier. First came the termination shock, where the solar wind slows from supersonic to subsonic as it rams into the interstellar medium. Farther out is the heliopause, the region where the pressure of the solar wind and the pressure of the interstellar wind balance. Beyond that, models suggest a bow wave, where the heliosphere's motion through the galaxy disturbs the gas ahead. No one expects a single crisp border. No one predicts a perfect sphere. The edge becomes a stack of overlapping zones, each defined by which influence dominates. Tonight, we're going to use that same mental model for the cosmic web. Our galaxy does not sit inside a spherical bubble with a glowing wall called the local void. There is no membrane, there is a gradual transition from underdense space with fewer galaxies than average, through regions where the density climbs toward the cosmic mean, and then into the bright knots and filaments where clusters of planets and stars accumulate. Cosmologists define this pocket statistically and dynamically. Statistically, by counting galaxies in large surveys and asking, is this region emptier or fuller than a random patch of the universe? Dynamically, by watching how galaxies and dark matter flow over billions of years, falling toward overdense filaments and draining away from voids. The boundary of the local void is where that flow changes character, not where something solid blocks the way. Galaxies cross these boundaries, matter streams out of voids and into walls and clusters. Over a Hubble time, a galaxy like the Milky Way can feel tugs from both its local underdensity and the larger scale web beyond. By the end of tonight, you're going to understand that our isolated pocket is more like a slowly shifting current in a vast ocean than a sealed-off room. And just as Voyager's crossing of the heliopause did not sever the sun's gravitational pull, leaving the local void does not flip the laws of physics. The same gravity, the same dark matter, the same cosmic expansion operate on both sides. What changes is which effects dominate, local flows versus global Hubble expansion, nearby underdensities versus the average cosmic background. Boundaries in cosmology are regime changes, not prison walls. But if there is no hard shell around our pocket, then how could living in one underdense stream of this ocean possibly trick scientists about the entire universe, and what would it take to notice the illusion? The illusion only works if you forget one thing. Different scenery does not mean different physics. Tonight, we're going to step outside our pocket and ask what the rest of the universe is actually doing. First, the rest of the universe looks different, needs a very specific meaning. It does not mean other regions have new forces, alien equations, or a second kind of gravity. It means that far from our void edge neighbourhood, the local density of galaxies, the shapes of clusters, and the exact merger histories can look wildly unlike what surrounds the Milky Way. One region might sit deep in a filament drenched in galaxies, another might float in the centre of a vast void. Same universe, different weather. Why does that happen? Because the early universe was not perfectly smooth. The cosmic microwave background shows tiny temperature ripples, 1 part in 100,000. By the end of tonight, you're going to understand that those ripples are the seeds of everything. Gravity pulls slightly denser regions together. Expansion stretches emptier regions apart. Over billions of years, the same rules that shaped our pocket sculpt filaments, walls, and voids everywhere else. This is the cosmic web. Surveys like Sloan Digital Sky Survey and DESI map hundreds of thousands of galaxies and reveal a pattern that repeats. bright filaments, massive clusters, and yawning voids tens to hundreds of megaparsecs across. No one predicts a perfectly uniform fog of galaxies. The web is the expected outcome of standard physics applied to those tiny primordial fluctuations. The details change from place to place. The statistics do not. Here's the key pattern interrupt. When astronomers look on very large scales, they stop asking, "What does this exact patch look like?" and start asking, "How often do we see voids of this size, filaments of this thickness?" In many directions, the answers match. The distribution of structures follows the same statistical rules, supporting the idea that the same gravity, the same expansion, the same particle physics operate far beyond our horizon. That's where our local underdensity fits in. The local void, or KBC void, spanning hundreds of millions of light years, is an underdense patch superimposed on this global pattern, not a special realm with its own laws. Some scientists have even explored whether living in such a dip could bias our measurement of the Hubble expansion rate, nudging local values higher than the cosmic average. Expectation versus reality. The pocket can trick measurements. It cannot rewrite physics. Now, let's begin to think of it like this: weather versus climate. One city has storms, another clear skies, another a persistent wind. Yet the same thermodynamics, the same fluid equations govern air everywhere on Earth. Our pocket's cosmic weather looks unusual, even isolated, but the universe-wide climate remains consistent. The next step is to ask whether our strange weather is an accident, a selection effect, or something deeper. So let's zoom out and pin down what this strange cosmic weather report really told us. Tonight, we're going to turn the whole journey into 7 clear takeaways, so this isolated pocket stops feeling like a paradox and starts feeling like a clue. First, the universe is not a random spray of galaxies. On the largest scales, it settles into a cosmic web, bright filaments, dense clusters, and yawning voids. Our solar system rides a galaxy that sits near the boundary of a significant underdense region. Not in the deepest emptiness, not in the richest city of galaxies, but right along the edge where filaments fade into a local cosmic suburb. Second, that underdensity matters for measurements. The local void, and possibly a larger KBC-like void spanning hundreds of millions of light years, changes how galaxies around us move. It can make the local expansion look faster, biasing the Hubble constant that scientists infer from nearby supernovae and galaxies. The contrast is sharp. Expectation says one value, observation from our neighbourhood leans higher. But this doesn't overthrow global cosmology. It tweaks the local reading on the speedometer, not the underlying engine. Third, the early universe, as seen in the cosmic microwave background, looks almost eerily uniform. Fluctuations are only one part in 100,000. No one predicts that such a smooth beginning would stay smooth forever. Gravity amplifies tiny ripples. Voids like ours are late-time products of that evolution, the natural low-pressure zones where matter drained away into filaments and clusters. Fourth, simulations back this up. When computers evolve billions of particles of dark matter and gas under gravity, they naturally generate filaments, clusters, and voids with a wide range of sizes. Environments like ours appear in those runs, not on every corner, but not once in a universe either. By the end of tonight, you're going to understand that we are somewhat special without being cosmologically unique. Fifth, Anthropic reasoning enters here. Observers cannot arise just anywhere in phase space. They need long-lived stars, stable planetary systems, and relatively calm gravitational neighbourhoods. A galaxy perched near a void boundary may get a quieter merger, history, and a gentler inflow of matter, making complex life more plausible. Sixth, that leads to selection effects. Out of all the regions space can offer, observers are more likely to find themselves in those moderately special pockets that balance isolation with richness. Our patch is underdense but not empty, connected to the web but not crushed by it. Seventh, understanding this pocket does not separate us from the rest of the universe. It sharpens the map. Just as the heliosphere's boundary revealed how the solar wind meets interstellar space, our local void reveals how small-scale cosmic weather sits inside large-scale cosmic climate. No one expects a single galaxy's address to matter. Absolutely no one anticipates that by measuring it carefully, we might glimpse new physics in the tension between local and global expansion. Now, let's begin to ask what that tension is really telling us. That tension only really lands when you can picture where you are. Not just on a planet, not just in a solar system, but inside a layered cosmic address that runs from local quirks all the way out to the smooth edge of the observable universe. Tonight, we're going to build that address step by step, not as an abstract diagram, but as a mental zoom out you can replay every time you look up at the night sky. Start at home. Your solar system orbits inside the Milky Way, a flat spiral of a few 100 billion stars, about 100,000 light-years across. From here, the galaxy feels like everything, but pull back, and the Milky Way shrinks to one bright point among dozens in a loose swarm of galaxies called the local group, maybe 10 million light-years wide. Keep zooming. The local group is not floating in isolation. It sits along a filament, a narrow, elongated river of galaxies and dark matter. That filament runs right along the edge of a vast underdense region, the local void, or KBC void, hundreds of millions of light-years across. No one expects our galaxy to live on the lip of such a bubble. Absolutely no one anticipates that this could matter for precision cosmology. By the end of tonight, you're going to understand that void does not mean perfect emptiness. It means fewer galaxies, less mass, weaker gravitational pull. Picture the Milky Way not as hanging in blank space, but as part of a glowing thread of galaxies draped along the surface of this underfilled region, like a bright shoreline tracing the rim of a dark cosmic bay. Pull back again. That filament feeds into a larger structure, the Virgo cluster, and beyond it, the Laniakea supercluster, a basin of attraction spanning hundreds of millions of light-years, where galaxy flows all converge. Now, your local void is just one depression in a vast foam of voids and filaments, a three-dimensional cosmic web stretching for billions of light-years. Extend the zoom to the limit of what any mission or spacecraft can ever see. The web repeats, filaments, clusters, and enormous voids tens to hundreds of megaparsecs across, stitched together into a pattern that looks surprisingly similar in every direction. Wrap all of that inside a nearly perfect sphere, the cosmic microwave background, the faint afterglow of the Big Bang, uniform to 1 part in 100,000. Here's the crucial point. There is no hidden boundary where the rules suddenly switch. The same gravity that sculpts our local void sculpts the farthest cluster. The same expanding space that carries nearby galaxies away sets the scale of the CMB horizon. Before we get started on the deep implications, lock in this layered map. local oddities nested inside global regularity. Because the next step is to ask whether that elegant picture is telling the whole truth, or whether our position on the edge of a void is quietly rewriting what we think the universe is doing. Local oddities nested inside global regularity. That sounds like a problem. It is not a problem. It is a milestone. Discovering that the solar neighbourhood sits in an underdense pocket is not cosmology breaking down, it is cosmology levelling up. When the first galaxy surveys went out, scientists were thrilled just to trace the rough cosmic web, bright filaments here, dark voids there, planets and stars clumped along invisible threads of gravity. Now, measurements are sharp enough that a 10 or 20% dip in density across hundreds of millions of light-years shows up as a systematic bias in how fast space seems to expand. Expectation. The universe is homogeneous, so your local patch should be boring. Reality. The universe is homogeneous on huge scales, but your local patch comes with a personality. And that personality matters for precision. By the end of tonight, you're going to understand that seeing the quirk is a sign the instruments, surveys, and models are finally good enough to catch it. This is where the isolated pocket turns from annoyance into tool. Once you recognize that the Milky Way lives near the edge of a void, you can fold that into the equations. You correct supernova distances for the fact that nearby galaxies are sitting in a slightly emptier region with a slightly faster local expansion. You ask, very explicitly, how much that could shift the Hubble constant. Some proposed solutions to the Hubble tension lean exactly on this. Maybe part of the mismatch between early universe and late universe expansion comes from living in a local bubble. Now, let's begin the pattern interrupt. The void is not just a correction term, it is a laboratory. Sitting near a void edge gives a front row seat to galaxy flows, like watching cosmic weather blow across a continental boundary. On one side, denser filaments pull galaxies in. On the other, the underdense region lets them drift out more freely, as if the gravitational pressure has dropped. By tracking how galaxies stream from the void into surrounding structures, spacecraft and telescopes test how dark matter, dark energy, and the expanding background of space actually sculpt the cosmic web. No one expects every vantage point in the universe to be interchangeable. No one predicts that an observer deep in a rich cluster, bathed in X-ray gas and crowded galaxies, would see exactly the same local flows that we do. Absolutely no one anticipates that a lonely dwarf galaxy buried in the middle of a giant void would infer cosmic parameters in the same way as a spiral like the Milky Way perched on the edge. Every location comes with quirks. Ours happen to involve a nearby void, a particular pattern of galaxy motions, and a specific contrast between the smooth cosmic microwave background and the lumpy present-day web. That is not a cosmic insult. It is an opportunity to cross-check the standard model from an unusual angle to ask whether the global rules of the universe still hold when tested against a very local asymmetry. So, this pocket does not make the cosmos feel smaller. It does the opposite. It ties the home address of the solar system directly into the grand story of structure formation, where tiny ripples in the early universe grow into filaments, clusters, and voids. Tonight, we're going to use that connection to push on a deeper question. How much can where you stand change what you think the universe is? So, this pocket does not make the cosmos feel smaller. It does the opposite. It ties the home address of the solar system directly into the grand story of structure formation, where tiny ripples in the early universe grow into filaments, clusters, and voids. Tonight, we're going to stretch that story across human time, from a pair of 1977 rockets to 21st century maps of the void on our doorstep. The original plan is simple: 5 years, study 2 giant planets, then fade into the dark. No one expects those spacecraft to redraw the boundary of the solar system. No one predicts they will still be whispering from beyond the heliopause while telescopes on Earth redraw the boundary of our local cosmic environment. Yet that is exactly what happened. Voyager's path is the first thread. In the late 1970s, the edge of the solar system is mostly an equation in textbooks: a termination shock at some guessed distance, a heliopause at another. Then the data arrive. The solar wind slows later than predicted. The magnetic field twists in ways absolutely no one anticipates. The spacecraft cross into interstellar space far beyond the expected boundary, forcing scientists to rebuild their models of how our system sits in the galaxy. Now, let's begin the second thread. While those faint carrier tones come in from 120 astronomical units, wide field surveys start to map galaxies out to hundreds of millions of light years. What used to be a sparse star chart becomes a 3-dimensional web. Dense knots where clusters of galaxies live, long filaments where matter has flowed, and, between them, enormous voids where very little has ever formed. In just a few decades, the timescale of a single human career, the horizon jumps. The 1970s are about reaching the outer planets. The 1990s bring all-sky redshift surveys. By the 2010s, simulations and observations together show the Milky Way not just in a cluster, not just in a filament, but near the edge of an underdense region hundreds of millions of light years across. The same way Voyager revealed that the solar wind carves out a bubble in the interstellar medium, these maps reveal that gravity has carved out a much larger bubble in the cosmic web. And this is not the work of one visionary mission. It is thousands of scientists, engineers, programmers, and observers across continents and decades, teams that built radioisotope generators and 23-watt transmitters, teams that built CCD cameras, multi-object spectrographs and supercomputers to evolve dark matter and gas from the Big Bang to the present. Different tools, same question. Where exactly do we live in space and time? By the end of tonight, you're going to understand that there is a straight emotional line from a golden record bolted to a 1970s spacecraft to a color-coded map of an underdense cosmic void. It is the continuity of curiosity. A species on a small planet, in a modest galaxy, on the edge of a vast emptiness, using fragile machines and shared data to comprehend not just the boundary of the solar system, but the structure of the universe itself. And once you can see that structure, a sharper question appears. Does living on the edge of a void change what you think the rest of the universe looks like? Living on the edge of a void changes more than the view. It changes what you now know about the universe and how few people can follow you there. Before we get started on the next mystery, pause on this. You can now explain what astronomers mean by the local void and the KBC void, not just an empty region, but a genuine underdense pocket in the cosmic web, spanning hundreds of millions of light years, where there are fewer galaxies than the cosmic average, and the Milky Way sits right on the boundary. Most people imagine space as a random sprinkling of galaxies. You know better. Tonight, we're going to treat it like a 3-dimensional foam, dense filaments and clusters, vast, ballooning voids between them. A web, not a fog. You understand that our galaxy is not in the middle of a crowded metropolis, but more like a suburb pressed up against a cosmic countryside. You also understand why scientists care. If you live in an underdense region, galaxies around you feel less gravitational pull, so local space can expand a bit faster. That means when you measure the Hubble constant with nearby supernovae and galaxies, the result can be biased high. Expectation: one clean value for the expansion of the universe. Reality: a Hubble tension that refuses to go away. But you've seen why the void alone is not a magic fix. The underdensity of the KBC void helps, but not enough. It nudges the local Hubble measurement. It does not erase the gap between the nearby universe and the value inferred from the cosmic microwave background. By the end of tonight, you're going to understand that living in a bubble can bend the numbers, yet cannot fully rewrite the story the CMB is telling. You now carry a mental overlay that most people never see. The CMB shows a universe that was smoothed to one part in 100,000, a nearly uniform glow from when the cosmos was just 380,000 years old. On top of that, you can place the later time cosmic web, grown by gravity from those tiny seeds, and then mark out our local void as one unusual, but statistically allowed, fluctuation in that grand pattern. No one expects casual space fans to talk about anthropic reasoning or selection effects. You can. You've seen how observers are more likely to arise in nice pockets, not at the crushing centers of clusters, not deep in the darkest voids, but on relatively calm filaments near usable resources. No one predicts where any one civilization will appear, but absolutely no one anticipates that observers will be evenly sprinkled through every environment the universe can build. What you hold now is a secret map. Most people picture a simple, uniform universe with us floating in the middle. You see a lumpy cosmos, a foamy structure, and a small solar system riding the edge of an underdense bubble. And the real twist is this: once you accept that our pocket is unusual but not impossibly special, you can ask a sharper question still. What happens if some pockets aren't just underdense, but obey entirely different rules? Obey entirely different rules? Once that question is on the table, the scale jumps. Our underdense bubble is one pocket in the cosmic web, but some scientists think even the entire observable universe might be just another pocket in something bigger. Tonight, we're going to push that idea to its limit and ask, what if the rest of the universe is not just denser or emptier than here, but literally a different universe? The logic is the same move, applied one level up. First, local galaxies, then our void, now whole universes. If a small pocket can bias measurements of the Hubble expansion, a larger pocket could change far more. The strength of gravity, the charge of the electron, even whether planets and stars can form at all. By the end of tonight, you're going to understand why some cosmologists look at our isolated region and think, this might be practice for thinking about a multiverse. In models of eternal inflation, space doesn't just expand, it keeps inflating in some regions while other regions peel off as bubbles where inflation ends. Each bubble cools, forms a cosmic microwave background, grows galaxies and evolves a solar system bearing cosmic web. But here is the twist. No one expects all those bubbles to share the same fundamental constants. Slight changes in the inflaton field or in how extra dimensions compactify in a string theory landscape can set different values for the forces of nature in each region. Now, let's begin to see how anthropic reasoning stretches. In our local void, selection effects explain why observers are more likely to find themselves in regions where life can form around long-lived stars. In a string landscape with perhaps 10 to the 500 possible vacuum states, selection gets sharper. Out of an enormous menu of possible universes, only a tiny fraction will have a balance of gravity, electromagnetism, and nuclear forces that allows atoms, chemistry, and stable orbits. No one predicts those values from first principles yet, so some argue the only explanation is that observers can only appear in rare, habitable pockets of a much larger ensemble. Pattern interrupt. This is not just late-night philosophy. It feeds back into concrete missions and measurements. The same way a spacecraft mapping the solar wind helps define the heliosphere's boundary, surveys of the cosmic microwave background, galaxy clustering, and Hubble expansion are quietly testing whether our bubble looks like a typical patch of a single universe or something that hints at a multiverse background. From dark energy to vacuum decay, from one bubble universe to a possible sea of others, the path has been the same. Start with a local oddity, end up rewriting the map of reality. Tonight, we're going to close that loop by coming back home to this lonely-looking pocket on the edge of a void and ask what it really means to live here. We began with a mystery. Why does our galaxy seem to sit in an underdense region while the rest of the universe, from the cosmic microwave background to the distant cosmic web, looks smoother and more typical? Along the way, the picture changed. The expectation was that space should look uniform once you zoomed out far enough. The reality is a vast, foamy structure of filaments, clusters, and voids, where regions like the local void and the KBC void are not glitches, but natural outcomes of gravity sculpting matter over billions of years. By the end of tonight, you're going to understand that this isolated pocket is not a mistake. It is data. It is a clue that helped scientists test ideas about the Hubble tension, selection effects, and the way the solar neighbourhood fits into the larger system of the cosmic web. No one predicts that simply measuring nearby galaxies and supernovae could force a rethink of the universe's expansion history. Yet, that is exactly what this mission has discovered. Local structure matters. And through all of this, the emotional core never changed. A small civilization on a small planet circling an ordinary star in an ordinary spiral galaxy, perched near the edge of an immense void. Yet from here, with spacecraft, telescopes, and equations, that civilization can trace the afterglow of the Big Bang, map the invisible boundary between filaments and emptiness, and ask whether its own vantage point is typical, rare, or even necessary for life. The transformation for you is subtle but profound. The night sky is no longer a random sprinkling of stars. Those points are the bright nodes of a hidden structure, the visible edge of a web stretching hundreds of millions of light years, wrapping around vast dark basins where galaxies are scarce. Our pocket is no longer a cosmic accident. It is one chapter in a story that runs from quantum fluctuations in the early universe to the grand architecture of clusters and voids. In the end, the paradox dissolves. From an isolated pocket ringed by emptiness, a thinking species looks out and measures the universe, not separate from its story, but as one of the ways the universe learns to understand itself. So tonight, somewhere far above the Milky Way's plane, the rest of the cosmic web is still humming. The filaments are still threading from one cluster to the next. Galaxies are still falling slowly toward their nearest knots of mass. The local void next door, that quiet absence we sit at the edge of, is still mostly empty, still defining our position in the larger architecture by what is missing from it rather than what is present. The KBC void, if it is as large as some measurements suggest, is still inflating our Hubble constant by being underdense around us. And somewhere far beyond the surveys, The cosmic microwave background is still shining its quiet, even glow in every direction, recording a beginning we cannot quite reconcile with the lonely patch of space we currently inhabit. There is something steadying in that. The void does not know it is being measured. The galaxies in the next supercluster over do not behave differently because we are watching. The cosmic web is doing whatever it does at the scale of hundreds of millions of light years, and our position inside it is just one observer's vantage point on a structure too vast for any single perspective to capture. The data arrives when it arrives, the map gets a little more accurate every year, and somewhere out there the answer to whether our pocket is rare or typical is already encoded in light that has not yet reached us. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.